Alright, another draft physics video presentation. More on light because I have, I don't know. Discovered another truth about the slit experiments. It's just so obvious. And you're just like, obviously nobody ever thought about this stuff. This is just sitting there staring you right in the face when you see it. You just, oh, that's so glaring. How could we be talking about all this other horse shit when the answer's so obvious? So anyway, the troll, Mickey Farley, whatever, the cowboy, he actually made a civil video. I mean, it's, crazy physics in my opinion, an explanation of Huygens, and I can't make any sense of it at all. But it's just a physics video, so instead of all the gratuitous insults and all the ad hominem nonsense and all the lies, he just does his little physics thing. And so I figure when the pig flies, you should applaud, and say, very good, pig. Excellent. But of course he, forgot how to do it the next day, because the next day he's back to his little clowny stuff, back to the bullshit. So anyway, too bad. But anyway, so I'll link below to it just for the hell of it, because it's actually a physics video. Now, I can't make any sense out of it. It's incomprehensible, and it certainly doesn't address anything I've said about Huygens being a problem, in the sense that Huygens is a problem because you call it a principle, but you don't apply it as a principle. That's the problem. Okay, I don't care what nonsense you make up to split the single slit, right? This is, look, and the real point is just admit this is how it's always taught. That nobody on the internet is teaching it your way. They're all teaching it some other way, and that's the thing to be recognized. So you have these two experiments. Single slit, double slit, right? Now they had to contrive some, see, first they emphasized the double slit because that was the beginning of their quantum, and the whole idea of a single particle has to split into two and create two waves. And then they realized, oh, Newton's rings. Oh yeah, single slit does the same thing. So how do we make two waves when we don't have two slits? Ooh. And so they added an addition to Huygens, that has something to do with bisecting the single slit and actually creating two waves inside. And they interfere with each other in this traditional manner, and they draw it in the traditional manner, blah, 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 blah. And you end up with an interference pattern. Now, my objection is only, well, if you're going to say that happens here, how does it not happen here? And then they try to use an excuse, well, we never have this slit width is not this slit width, because when we do the double slit, we have, a micro slit of some kind or something. They use some excuse. But the point is that I can have the exact same dimensions for this slit as I can have for this slit and the double slit, and I'll get a perfectly coherent pattern that way. And the question is if you're going to use Huygens here, why aren't you using Huygens here? If Huygens bisects the single slit into two waves, why doesn't this slit create two waves and this slit create two waves? That is where I'm saying you have a contradiction. You can't call it a principle and then change what the principle does or what the principle means. So that's the objection. I mean, I clearly would also object to an infinite number of little wavelets, and then you bisect the infinite number into two to two sections and say this infinite number is doing this and this infinite number is doing that. All of that is also, in my opinion, nonsense. But anyway, so that's the point, the question, the paradoxical circumstance for which I find implausibility is that you have a principle that you're not applying consistently. I've said that over and over and over again. Principle has to be consistently applied. So anyway, so my revelation, I have often complained that they keep talking about this slit width being having something to do with the wavelength of the light, right? And it's never made any sense, because I'm saying, well, the wavelength of a light is 500 nanometers. Okay, I mean, that's 1/2 of a million, right? 1/2 of a million millimeters. It's really small. It's a small thing, 500 nanometers. It's, you know, it sounds like a lot, 500, but no, it's really not very much. Okay, it's really, I can't draw a line thin enough. That's how thin that is. So it's really small, that distance. And they keep talking like this slit width is 500 nanometers. No, it can't even be anywhere close to that. And if you want to get any kind of good pattern, it's got to be like a 25th, you know, one. It's got to be bigger. It's got to be like a quarter, 1/4 of a millimeter. All right, we'll give you a nice pattern, or even 1/8 of a millimeter. All right, so you know, you get a good pattern, and that's a long way from 500 nanometers. There's like 500 of those in this one thing. I mean, this one thing, there's 500 of them in 1/4 of a millimeter. There's a lot of them, maybe 5,000. So their numbers never made any sense to me. I mean, it just sounded like gibberish. What do you mean a slit width the size of the, you know, the wavelength of the light? Well, anyway, then the other thing that I've brought up even 10 years ago was, you know, technically when you're doing this, see, they always confuse you with this experiment because they talk, okay, here's some pattern and it's going, and they give you this idea that it goes for infinity, okay, that it goes, you know, you can just go on this straight line forever. And yeah, a straight line provides that for you, but you have to understand that when you're going at an angle, everything's getting bigger. So as the pattern, you know, you have a certain size, well, the pattern starts getting fatter and fatter. And this is why, you know, they finally made movie screens bent, is because it gets distorted. This is actually the same size and angle. You know, at the source, this is the same angle. The same exact angles are creating this big fat thing that created this little thin thing. So when you go towards your infinity, things get infinitely large. So it's not like there's more of them, it's just that every one of them gets gigantically huge as you spread in those bizarre angles. And so this experiment should always be sort of understood that what you really should be doing is seeing it on a parabola or a half circle. That when you're viewing it, these distances should all be the same distance, so you get the right pattern. And then when you think about that, well, that's all this thing is really about, right? Is that, you know, we can figure out that the slit width, okay, is essentially, so if I was to take this out and you were to understand the point sources as being, okay, this and this, all right, so if those were the point sources, you could understand that all you're really trying to do is measure the difference between the length of this line and the length of this line versus the length of this line versus the length of this line. See, now these two lines will be equal, and these two lines will be the most unequal, right? So you have your maximum inequality with these two lines at 90 degrees, okay, and at 0 degrees you have your maximum sameness, okay, in distance. So it's all a very finite thing. There's only so much difference. So the difference between these two lines in the typical two-slit experiment might be 200. I don't know, you know, doing the transition from micrometers to, I mean, from millimeters to micrometers to nanometers, you know, it does get a little complicated, especially when there's 500 of them or something. So, but I mean, they're physicists. They should have gotten this stuff right a long time ago. So all you're really saying in terms of what kind of pattern you're going to get is how many wavelengths are there inside of that difference in distance. That difference of distance will tell you how many bars you're going to get in your pattern. The bars in the pattern is exactly, okay, it's not even proportional. It is equal, okay, to this distance. How many wavelengths are in the width of the slit. So if you have the width of the slit at the wavelength of the light, that is if you actually make a 500 nanometer slit, okay, a tiny little slit, you'll have one. So you'll get the simplest pattern possible, which will be one on either side, and that's it. One fringe on either side. And if you go to 1,000 nanometers, okay, then you have two wavelengths, and then you'll get two on either side. That's all you're going to get. So obviously, as you go higher and higher, get wider and wider, you have more potential for more fringes. So the number of fringes is dictated by how many wavelengths there are between these 2 points. So again, these are the 2 sources. This and this are in fact the 2 sources, and you're just measuring. You could sort of understand, okay, I can understand anyway, that at this point, okay, these 2 lines would be less different than they were, you know, than these 2. These 2 are the most different. These 2 are a little less different. So now the amount and you're cutting into this distance is getting smaller and smaller and smaller and smaller. So the 2 lines are getting more and more equal, you could just say, as you go up this arc. And they're both equal, both the same length. So that's all you're doing is as you're turning, you're cutting deeper and deeper into that difference in the wavelength. You're just saying the lines are getting more and more unequal in their length. And the equality goes from being on phase to being off phase to being on phase to being off phase to being on phase to being off phase. So the difference in the length just means when do your lines match, when do your notches not match. So you could just say as these lines get longer and shorter, the position of the notches, so to speak, changes. But it doesn't matter. You can just think of it as rulers with notches, and the 1 lines up with the 2. You know, well, here would be like the 1 would be the same as the 15th marker on the other ruler. So 15 inches would line up with your ruler with the 1 inch on the other ruler. The notches line up, and that's all you're doing. You're just lining up the notches and creating phase and off phase. So anyway, so yes, understanding that if you got to keep this equidistant gives you the understanding that, oh, this isn't about some infinity. It's just about this very finite amount of distance. And how many times can you create a phase change in that finite amount of distance? And what tells you how many times you can is this distance here. So this distance has to have multiple wavelengths in it for you to have multiple fringes. And the wider you make it, the more wavelengths are in the space. The narrower you make it, the fewer, and that's why the pattern gets bigger and less interesting, is because you're changing the amount of change you can make is getting smaller and smaller. You can't make a significant change because there isn't enough distance to make the change out of. Yeah, so I'm trying to think of how this exactly proves their wave theory impossible, but I mean clearly it does identify the real point sources, which is the surfaces. And once you identify that as the real point sources, the wave theory kind of disappears as being reasonable, because this has nothing to do with 2 waves inside of this distance interfering with each other. It clearly just has to do with the length vector differences between the 2 points. That math works on the single slit, it works on the double slit, and it works on the diffraction gradient. So unlike their psi bullshit, unlike their wave function, this math works okay on all of the experiments. You don't have to change any principles. You don't have to change any rules. You just measure distances. What's the biggest distance between 2 of the surfaces? What's the smallest distance? And you'll understand those are vector lines. And those vector lines, the difference in these 2 lines, the length of those lines dictates how many places on this arc you'll be able to create in phase and then out of phase. And so that explains the experiment. And it's kind of just simple geometry. Again, like I said, this is so simple that how could nobody see it? How nobody recognize it's so simple? and yet they were so glued to a wave theory that it must be a truth that not a single thoughtful person with a physics degree ever sat there and decided for a moment to consider, well, what if it's not a wave? What if it's not some stupid humpy thing? Because, the humpy thing is just going to get, trying to make waves interfere. It's just going to make a mess of the analogy. All right, so another thing I thought of. I mean, this seems to me to be nail in the coffin kind of evidence that this has nothing to do with waves. It just has to do with distances between these points. Come on, people. All right, anyway. All right, so another thing I thought about was I barely mentioned this before, I think, in a video, but it just glared at me a little bit. So you have the photoelectric effect, and they often describe this as being, well, electrons have to get hit with a certain amount of energy to pop them out of a box, So that's how they describe it. I mean, it's obviously, in my opinion, kind of a poor analogy. I think the rational analogy would be to say electrons are attracted to protons, attached by a pressure force, external pressure. So for an electron to be liberated, it has to somehow be hit with enough energy to break it free from its weak bond. It's not a strong bond, it's a weak bond. In most of these metals, there's these extra electrons are just stuck, weakly. They're not part of the atomic structure of the atoms. They're extra. Well, anyway, and so essentially you have a tether, and all you do is, the idea is you have to hit this electron hard enough to break the tether. So the electron breaks the little tether and is free. So you can think that, to me, is a much better analogy. And so why does infrared light, I can send a whole bunch of it, a red light, and it'll do nothing. It won't break any tethers. And then I send a little bit of ultraviolet, and so I send a little bit of that, and somehow that accomplishes the task. So that's the question. Why is there this line where nothing happens and then the line goes like this? So if I use X-rays, I get even more effect. So the tighter the frequency, the more effect I get, is what is the obvious, oh yeah, that's the first impression. But that impression is just a first impression, right? I mean, you're supposed to be doing physics, you're supposed to be saying, well, maybe there's something else to do with this besides just frequency. All right, but I'll say that frequency does have an obviously you can put a lot more energy in a smaller space. And so I've used this tipping point argument that the key is you got to hit this thing more than once. That is, when you hit it with one piece of energy, you can understand that you're stretching the tether, right? So you get it to this position, and now the tether is stretched. And then if you can hit it again before it relaxes and gets back, if you can hit it again, then you can break the tether. So the idea is that the problem with infrared is that it's just too much distance between these, between the nodes of the wave. The wave doesn't hit it fast enough, soon enough, and the tether pulls it back, and then it just keeps pushing it, but it can never break it because the frequency isn't high enough. And I think that's a perfectly reasonable argument. So what you're really saying is that you have to hit the electron twice within a certain period of time, and that breaks it free. And so to me, that's a reasonable way to look at it. You got to hit it once, and then you have to hit the same electron again before it relaxes to break it free. So that seems a rational explanation. So, so obviously this frequency thing would matter. But then the other thing you have to consider is that's only one part of it, really. Because the other part of it is that what we also know is that the infrared light has big polarization. It spreads over a bigger surface than the ultraviolet light. The ultraviolet light is a narrower surface. So not only does it have more elements for a period of time, right? In the same amount of time, there's more energy in this ultraviolet stuff than there would be in the infrared stuff, because the infrared stuff has to be further spaced. The spacing has to be larger, so obviously there's less of it in a period of time. But it's also polarized smaller, half as much polarization. So you could sort of understand that if there was an electron and it had to be hit by something, well, this spreads over a lot more area, so it's less likely to hit the electron. There's a lower likelihood. Where this, these two elements at the right timing, are more likely to be able to hit a electron because they're coming in a narrower package, and so the smaller package means they're more likely to, twice as much at least, to, a 2x increase. It's probably more than that because you're confining it in two directions in a sense. Even though polarization is just in one dimension, it's still one dimension in the where you can turn that one dimension in a lot of different ways. So you still end up with it doesn't matter how much, 2.5 here. It's a higher percentage likelihood of being able to hit one of those little bits. Now, the other thing they found over time is that if they do hit it with a lot of radiation, a lot of infrared, that they can in fact kick some electrons out. And that argument would be is that if you send enough rays, enough of these little wavy things, if you prefer, which still again doesn't make any sense, some portion, like the bottom of the hump on this one, the up and the up on this one are at the right timing, and they'll both hit and soon enough to knock it out. So you can use more than one photon will get the job done instead of it being just one photon. For one photon to do it, you need the package that's in a smaller container. You need the energy to be in a smaller area to have a hope of hitting that little tiny electron twice in the right sequence. So anyway, it was just something that I realized that they don't even consider polarization as a function of light. I mean, all they think about is this frequency thing. And this gets to the subject, which I think was just such wrong-headedness when they did the de Broglie thing of deciding that frequency equals momentum. So use the P for momentum for whatever reason, and momentum equals mass times velocity. So they turned frequency into something that had mass and velocity, and that's not what it is. If frequency isn't velocity and frequency isn't mass, it's just a breaking of there's no need to do this. This is one of those equivalency things they just should never have done, this derivative math that they are so dependent on. Well, the danger of doing these derivatives is creating equalities or proportionalities that aren't consistent over all circumstances. They only mean something in one circumstance. They don't mean anything in every circumstance. And that's what they've, it's a terrible mistake to put this equal sign here. It's the energy frequency only matters when you need to tip something or when you need to break a tether. Then frequency matters. But when an electron is just being an electron, it doesn't matter. And when you're moving it in some other direction, not its tethered direction, frequency is irrelevant. And what's really going to matter is the fact that the energy is moving the speed of light, and that it has a h constant, in the sense the speed of light at a consistent mass. All the little photon bits weigh the same amount. They all are just quanta. The ones in the red light, the ones in the blue light, the ones in green light, doesn't matter what color light it is, the little bits are always the same, and all you're doing is changing the arrangement in which you send them, in terms of you're changing their polarization, how much they're spread apart, how much you move the gun as you were shooting the bullets, or how far up and down the antenna you went to make the signal. That's the polarization. And the other feature is just the distance between them. And those things have to be understood as different things. But again, it was just never even considered that the other feature that is different between infrared light and ultraviolet light, the other important feature is the feature of polarization, because they have completely different, okay, ultraviolet, I guess just UV. Yeah, they have very different polarizations, and substantially different, and that is part of the reason why one does something the other can't do. And this, like I said, for X-rays, it's even smaller polarization, so obviously they're even more likely to be able to hit the same electron more than once. Alright, so I think that's enough of that. So I will play some of this, the end of this video. Didn't make, like I said, yeah, there's no, Huygens principle is, I can't make any sense out of it, in the sense that the whole point of it is to try to make this round, find an excuse to make a wave, a flat wave, into a round wave. And Huygens was originally, this wave theory of little waves and making the new wave was originally for the purpose of understanding refraction on surfaces, and that the light came in and it created these little bunch of little tiny waves, and then you could explain why the light bent because of the way the little waves behaved. But anyway, in a single slit, it doesn't do you much good to imagine a bunch of little waves creating the next wave front. And the reason why they make it infinite, right? The reason why they say there has to be an infinite number of these little waves is the obvious. Like, you could understand it. If I was to make a bunch of these little waves, they wouldn't create a flat wave. They'd create a lumpy wave, right? I mean, it wouldn't be flat. So if you're going to take something flat and say a bunch of little waves make the next flat wave, you need to make an infinite number of them for all of these waves to be so close together that their peaks, create a flat line. So you have to have an infinite number of them to create a flat line. So I mean, that part just, you're just saying that doesn't make any sense. I mean, that's just too silly. So anyway, the idea is that flat waves come into the single slit or the double slit, doesn't matter, and magically you end up with, this bowed wave. Now, that doesn't help them because that's not an interfering wave. But there's also no reason to think there's any reason why light does this, right? Why wouldn't light just create a flat wave that goes flat right up through and goes straight through and stays flat? There's no reason to think of it. Why? There's no friction here with photons. That's what water uses, is friction. And then they had to take it a step further because, like I said, that single wave isn't going to give them an interference pattern. So somewhere in this process, they had to create this notion that this wave coming through had to get bisected into two waves, and that somehow now you still have to make them into round waves to create an interference pattern. And none of it, in my opinion, has any kind of reasoning, or why should I believe the universe does that? And then again, if it does it here, why doesn't it do it with the double slit? Why doesn't it create four waves? Why don't they draw it with four waves? I mean, first, they don't do it because it doesn't work. It's not going to create the right pattern. But, there's just no consistency. So this is what he's trying to explain, is why this part is broken into two. And he's doing it by drawing some sense that in T1 it's going this way, and at T2 it's doing this. Well, that's a convenient. Yes, it's on and off, but T1 and T2 don't go through the slit at the same time. At any one time, the best you could say was it's on here, and the T2 it's off there and it's on here, right? And at T3 it's back on here. That's the best you could do, but you're not. This is just incomprehensible, frankly. But, like I said, at least it's civil.
It's traced out. It's going to make one full phase of the wave. And then the contributions from each of these points. So let me just back up. So the first thing we could do is just take a finite selection of points. Okay, so that this, we would say, well, if this is lambda here, and this is minus lambda, then we could just add up the height of each of these vertical lines here and add them up and then divide.
Minus lambda? I don't even think I've ever seen a minus lambda, but whatever, fine. Okay, so now he's almost talking like polarization, making the wave this way and this way. I mean, having lambda not going this way, the way the frequency's going, but instead having it as an amplitude. So, hell if I can understand that.
Them by the number of points we've chosen. And that's going to give an approximation for the height of the wave at the point P. Right? Because if this point here interferes with this point, we get cancellation. And it looks the way that I've drawn it, that all of these points are just going to cancel with each other. Okay, but that wouldn't necessarily be true in every case. If we chose a different P, like let's say we chose a P so that the image traced out is like this, then certainly this point and this point is going to cancel. This point and this point is going to cancel. But then we're still left with positive height here and here, which do not cancel out. And so we
yes, by arbitrary eraser. So I can just erase my problem and put it somewhere else to make it asymmetrical. Why don't I just have an odd-numbered infinity versus an even-numbered infinity? Right? If I create an infinite number of points, I can create an even infinite or an odd infinite, right? And that can leave me a remainder. And remainders are so convenient for putting right in the middle. I mean, that this cancellation argument makes no sense because it's completely dependent on whether you think there's an even number of things to cancel or an odd number of things to cancel.
Actually get positive height magnitude at the point P. Okay, and then as we let T vary, as we increase time, then this wave is just going to bounce up and down. And the way, these points are going to oscillate. But then remember, we're taking the square of the magnitudes when we calculate the light intensity of this light source.
So again, the intensity is irrelevant. I'm trying to figure out why you have two waves coming out of a single slit. All right, and that part you didn't explain anywhere in this video.
So in the way that I've drawn this graph, you will get light at that point. But if you move down a little ways down the screen, you get no light, because look what happens if I increase P enough, I'll just get total cancellation. Okay, and so what I get is this, this point cancels this point cancels this point, and so on. Huygens' principle says that although this is a good approximation for the wave, the magnitude of the wave at each point.
Well, it's really not a good approximation. That was the whole thing. He said this is based on Khan Academy's video, and Khan Academy admitted that what they were saying didn't make any sense, and they had to redo it. And then even when they redid it, it doesn't really work. So they're sort of mushy on this subject, to tell you the truth. Their track record isn't too frickin' good. So again, this approximation crap, vaguely it's sort of like, that's just not good enough, especially for a cornerstone contention that we've put some nail in the coffin and proven that light's a wave because, well, in one circumstance it looks like a water wave, but the rest of them it doesn't. So it matches a little bit in the two-slit experiment, not really that much because the two patterns don't show up in water. But it doesn't match in a single slit, and it doesn't match in a multiple slit. So it's not a very good analogy. It's not a very good approximation. It's not a very good theory. And again, you're so desperately trying to force it to be a good theory. And I just would wonder, why are you trying to force it this desperately, where you're just making up infinite point sources and all this other crap? I mean, why are you doing this? Why can't you just admit that, yes, the physics is founded on mush? That the foundational experiment is very mushy, and we haven't got a good explanation. And we don't really want to consider, some other mechanism, like the surfaces being the cause.
The exact solution is when you take the limit as the number of point sources goes to infinity. And if you know any calculus, you know that this value is going to be the area under the curve. Okay, so we're actually, what we're doing is we're measuring the area under the curve, with the caveat that area under the x-axis, under the horizontal axis, is subtracted, whereas area above is added. And in this particular case, what we're getting is sort of the integral of lambda times sine, or in this case, sine of, just for simplicity, let's say this is 2 pi.
All right, well, never have I seen anybody use an integral to do the single slit. So, fine, you can choose to do that and tell us that that's what they actually are doing, is an integral across the entire slit of an infinite number of point sources. But I don't think I've ever seen that, frankly. Because all you end up with is 2. And the 2 are the dimensions of the slit. The only distance that matters is how wide is the slit. That's it.
So this is x.
How far away are the 2 surfaces? That's the only variable that means anything here. How far away are the 2 surfaces? So if I use the single impediment, my finger, or I use, the double slit, where I put all of those the same width as my fingers, or I get rid of the slits. Yeah, I get rid of the slits, and I just, single impediment, or I just have the slit of the same width. Those 2 things are the same thing because the surface distances are the same thing. I mean, how do you counter that simple observation? That what makes there's 2 experiments that are just, they'll give you the same practical result except for the central maxima not being as bright. So the only thing you'll change is how bright the center spot is. But I mean, the 2 experiments will create the same result. A slit that's the same dimensions as an impediment. You'll get the same math. You'll end up with the same pattern with these 2 experiments. They'll give you this same pattern, equal pattern, except for this, like I said, the center. Obviously the center here is going to be wiped out because there's not going to be any way for the light to go through the impediment and make this brighter. But otherwise, you'll get the same number of bars with this experiment and this experiment. So, how do you counter this simple logic of that what's in common between these 2? What do these 2 experiments have most dramatically in common? Oh, the distance between the surfaces. Not the width of a wave. There's no width of a wave here, right? I mean, the wave can be infinitely big on either side of this thing. There's no wave size when you're using an impediment. So how does wave theory is more sensible than understanding its surface theory? The wave here is confined. The wave here is not confined. How do you say this wave is going to be this size, and then I'm going to Huygens it and make it this size? How do you get 2 little Huygens waves coming off of this single impediment? How does your theory work? How does a Huygens waves, little waves? Sorry, I don't need 2 of them. How do little waves, the same size as this impediment, come off of these sides when there's nothing there to create that? How do they end up being the same? How do these 2 waves equal these 2 waves? It doesn't make any sense. I mean, this is clearly just about the distance between these thinking surfaces.
From 0 to 2 pi dx. And as long as we're integrating from 0 to 2 pi, it's always going to be 0, right? Because we just get cancellation. Right, this is equal to, negative cosine of 2 pi plus lambda cosine of 0, which is, of course, just 0. Okay, but notice that this did not depend on all.
Right. So again, this is more this cancellation, except for, this little remainder here in the middle that breaks the wave into 2 waves, so I can draw 2 waves interfering with each other. Again, it just doesn't explain how you ended up with 2 waves
at all on our time t sub 0. So, if we had instead integrated at a different time, or it was in the middle of a phase, we would still get cancellation. I'll show what that looks like. So let's say we were in the middle of a phase, so it sort of did something like this, and then, okay, so that's not really to scale. Something like that. Okay, what have you?
I mean, what does this drawing have to do with it? I mean, you're taking time and moving it this way as if it's a wavelength. And you're just saying, okay, the wave is on at one point and it's off at another point. Yeah, we already know that. We're trying to figure out the stuff going this way that's creating two waves. I mean, you telling me the wave is on and off, I already know that. I don't need to see that. That's not what's interfering, frankly. T1 and T2 are only relevant, okay, once you start making the length of the lines different. But again, that's kind of obvious. That's just the geometry. Again, that works for the jamming experiment. It works for a lot of different things. The fact that there's a phase change isn't the part that's being disputed. The part where you have two waves that are creating the phase change is the part being disputed. That you have some mechanism that creates two waves that can interfere with each other. How else to say this? I mean, you can't make one wave have two time elements. That's cheating.
Then we get addition here, and subtraction here. But this is still going to add to, 0, because what we've removed over here is just this endpoint here. So this is just that area. This area here is equal to this area. And that's true for every value of t. And so we always get cancellation at particular points. And that, in particular, those are the points on the diffraction pattern on the wall where we have dark bands. Okay, so that's Huygens' principle.
No, it isn't. Okay, the end of the video. Well, anyway, I appreciate that it was just a physics video, but again, it just wasn't Huygens' principle, and I could play the earlier bits, but there was just no explanation of where the two waves come from.
A lot of times in math, it's easier if you just take the limit to infinity.
So again, that was a funny statement. I thought it was a little bit funny. In math, it's easier if you make infinities. Yeah, wow. Sorry, no sale. I don't see how that could ever be true. I mean, if I have to, if I'm at work or something and there's an infinite number of, tasks for me to perform, I can't see how that makes work more fun. But anyway, just not worth the trouble. Let's see, Gary is a coward who won't address the argument. Well, I don't know what your argument is. Again, you're the one not addressing my argument. My argument is, if Huygens happens, why aren't you doing it to the double slit? And you're not. You're not using the same principle. You say it's Huygens, but you're doing Huygens in a different way, because you don't create two waves in each of the openings. And therefore, it can't be the same principle, can it? No, it can't. All right. So, probably enough of a video. So anyway, just every day something new occurs to me. That answers. So I mean, that's just more evidence that I'm on the right track. In terms of it, just like I said, it just keeps answering questions. Maybe that's just because their theory is wrong, and you just find more and more defects. As soon as you find one, all the other ones start to line up. The same kind of broken logic, and especially when they do things like make equivalencies between frequency and momentum, which is just a huge mistake. I mean, I can't even, just gigantic mistake to think the two things are the same thing. Because in some circumstances, frequency is going to matter, and in some circumstances, it's going to be completely irrelevant. Alright, anyway. Till the next time. And such. And so forth and whatnot. Well, I don't think there's anything else that needs to be reported on. Yeah, that'll do.